Okay, thank you for that nice introduction. Very nice to be here in person. So I hope everyone's ready. We're going to talk about cosmic dust for the next 2 hours. No, we're not. Okay. So this is my penance. For 25 years, I've been I'm working on cosmology, not dust. Okay, so I'm going to cover a lot of the same ground that Lecha covered this morning. Where's Lecha? I need her as a reference point. There you go. Okay, so I know where to point here, where to assign blame. Okay, but from a different vantage point of someone who's been kind of designing and building these instruments for the last 25 years. Okay, and let's start with maps. Everyone likes a good map. It turns out it's a good way to learn about your universe. So simply put, a simple map would be to just measure the positions of things in space, so let's say planets or stars or galaxies, and ideally, sure, if you could measure their velocities as well, you measure their velocities, put all these things on a map. Historically, this has been very useful for physics, where we've measured these properties in the solar system, and then you demand a consistency between that map and what you've learned in, let's say, first semester physics. Who's a freshman here? Do we have any freshmen here? Okay, got some freshmen, right. Okay, so this should look familiar, right? Like you write down Newton's laws of gravity. So you can demand that you have consistency between these maps and what you've learned in your first semester. And hint, it doesn't exactly agree, right? Maybe you haven't gotten there yet. That's later, okay. But through these maps of the solar system, we have made fundamental advances in physics, and just in the 1900s, for example, the confirmation of general relativity by looking at the precession of the orbit of Mercury, by looking at the deflection of light around the sun. So again, just very important as far as just these fundamental discoveries of the laws of physics. Okay, we can do the same thing making maps of the universe, right? So Lecha showed an example of this where you're looking in the early universe, you're seeing the surface of last scattering, the cosmic microwave background. We can make maps at slices of time throughout the universe. And again, try to make as many observables as we can for positions and velocities of these points of light. So for us cosmologists, when we look at galaxies, we just, as just a disclaimer, we forget about all the gastrophysics. We're just like, yeah, it's just a point. Put it on the map. Okay, that's just what we do. And then these maps, again, it's essentially the same process of if you have some initial conditions of the universe, any initial conditions, whether they're Gaussian random phase or not, they could be something else, but that you still have to have a consistency in this evolution of an early time map to a late time map. Okay, and so the consistency is with what we understand today as far as what makes the universe in terms of the fundamental particles and the fundamental forces. So the standard model for elementary particles, this is it. So we've filled out this chart just 10 years ago with the discovery of the Higgs boson. So those are the fundamental particles that we know about. You mix them all together, that gives you the periodic table of elements. It basically gives you every particle that we detect in the universe today. It also gives you the anti-elements, right? So you can take different combinations of these quarks. I mean, to us, it's like, yeah, matter, antimatter, whatever. It's all normal baryonic matter. It's all made out of just some different combination of these fundamental particles. Okay, and then the forces. So second semester physics, you learn about well, maybe you don't learn all of them. Okay, at least by third semester, the first few semesters, right, you learn about these four forces, right? So, right, first semester, second semester, third semester. Okay, there you go. So this is supposed to be, when people talk about what's the standard model of physics, It's basically those particles, these forces, mix them together. Yes, there's some detailed numbers that you need to know, but that's basically it. Okay. Then experiments. Yes. Oh, turn up my volume. Okay, sorry about that. Is that it? Oh, sorry, it was just in the way. Okay. So there are the lab experiments and then the cosmic experiments. And as Leach said, they're kind of different experiments in that the cosmic experiments, we're cutting off my screen a little bit, aren't we? Cosmic experiments, we're not actually going and mucking with the universe, right? We're just passive observers. But we can observe very large scales, obviously, and we can also look back in time. We can see what the universe looked like billions of years ago by looking at objects that are billions of light years away. Okay, then here's where we are today. Those maps, they're not consistent with these known fundamental particles and forces. So that means we're actually going beyond the standard model. So to the particle physicists, they talk about it as it's BSM physics, which just means it's beyond the standard model. Sounds cooler when you say BSM physics, though. So cosmologists, essentially this is what we're doing, is BSM physics. Okay, and what do we know so far? Well, we know most of the mass in the universe is not that baryonic mass, but it's dark matter particles. First discovered by Vera Rubin in the 1970s, and others, looking at galaxies. And really the first strong evidence was looking at the rotation curves of galaxies, so just how stars orbited around galaxies. And given where the light was at the time, we knew there must be more mass out here than just the light could account for, because the stars further out in a galaxy were moving just as rapidly as the ones close to the center of this galaxy. At the time, we didn't know that this was non-baryonic matter. So this is kind of pointed to as like the discovery of dark matter, but it could have just been like black holes, or it could have just been gas that we didn't see for some reason. It could have just been rocks, right? Actually, that would have been a very easy thing to hide if you could make them. And that would account for these rotation curves of galaxies. Since then, we now know unequivocally that it's not baryonic matter. Okay, and I always say this, someone who should have gotten the Nobel Prize, and now it's too late. Okay, dark matter, not yet found directly in the lab. So this is an experiment deep underground in the Dakotas, trying to detect them directly. But we are learning more about dark matter through these cosmic surveys. And in fact, we can actually map out today on large scales anywhere where the dark matter is clustered. And it's basically clustered where the luminous matter is clustered. Okay, so if I go back to what are the known particles, what are the known forces, we know this is incomplete. There's at least one unknown dark matter particle, but it could be a lot of different particles. So there could be this very rich physics in dark matter space that we just don't know about yet. So when you watch science fiction movies where they have your dark matter people or whatever, like, could be as far as we know, right? There could be this very rich physics that, basically doesn't interact through strong forces, weak forces, interacts gravitationally, but maybe we're cohabitating the universe with some other whole dark matter world. But we do know on large scales they're clustered with us. Okay. So those are the particles. Then we come to the forces. And the other thing we know today is that dark energy accounts for most of the mass energy density of the universe. So this, people like to point to this as a discovery in 1998 of distant supernova explosions being fainter than they should have been. And I'll say, I'll freely admit, I didn't actually believe this in 1998, so a lot of my colleagues did. I just sat back and like, you know, I just published this map of dust. I bet there's some dust in the distant universe. It absorbs a few photons. There's no way there's dark energy. That would just be crazy. Okay, I was wrong. Everyone else was right. So don't bet the same way as me. So we know unequivocally today there is another force. So we know because they get the Nobel Prize eventually, though they didn't get it in 1999, right? Okay, so it took a few years. But we know that something is happening where there's today in the more recent universe, there's too much space between us and galaxies, and this is due to an accelerating expansion of the universe. Okay, so this appears to be another force. Again, it dominates today. And then at the end of my talk, I'm going to get to, we think there was also another force very early in the universe, in the first moments after the Big Bang. That was the inflationary force. And then together, it would be these 6 forces that then explain the universe. Okay. So we know that there's this dark energy component of the universe. We can write down how we think it would behave. I'm not going to talk for Leach, I think, has already covered this well enough. But there was this discovery of dark energy in 1998. Since then, we've primarily just been making observations that really solidify this picture of the universe that, yes, there is this other force. Yes, it's been pushing the universe apart in the recent billions of years. But it's really only in the last few years where we've gotten to the next generation of experiment where it's like, okay, now let's turn this into a precision science as far as measuring what dark energy is. So we're really just crossing this experimental threshold today. Okay, so this is, I mean, if this isn't clear, this is why it's so exciting for us, because we can finally measure things, okay? Okay, so now I'm going to go through and talk about just the different methodologies that we have for mapping the universe from the nearby universe. Or in the nearby universe, it's actually pretty easy. We have all these bright galaxies out there. We can map them. As you go back in time to the early universe, there was a point before all these stars were formed where the universe was primarily just neutral hydrogen gas. This is another part of the universe that we can map, but it's more challenging. Then there's the cosmic microwave background, which was the surface of last scattering. That has been measured well. And then finally, a neutrino background. OK, so let's walk through these. First, a point to make is when we're making maps, they're never simply X, Y, Z. Like, I wish we could do that. Just bounce a laser off the nearest galaxy and wait for it to come back. You'd be waiting for a long time. So the nearest galaxy being, you'd be waiting just a few million years. So you could try that, but I don't advise that. So instead, we're making maps where these galaxy maps, in general, what we're doing is we're making measurements where it's 2 angles on the sky, and then a distance where we're not really measuring the distance, but we're measuring the redshift. And what the redshift is, it's a combination of the distance plus a velocity along your line of sight just from that galaxy's motion, which we think would be induced by the gravity field, so the gradient of the potential field. So those are the maps that we're making. the other thing about these maps is you've preserved information from the early universe. So you have all these features in the map that have persisted since early in the universe, except on small scales, like in this room. This is not what the universe looked like 13.7 billion years ago, obviously. And on scales somewhat larger than that. So when you go onto scales that are larger than galaxies or groups of galaxies, what we say is it's thermalized, or at least it's gone nonlinear, meaning it's an evolution where it's really mixed up those initial conditions, and for the most part, you've erased that information. Okay, so we call those the nonlinear scales. Okay, so making these maps for the purposes of cosmology, so I kind of put these in two major buckets. Okay, there's a bucket where you're making point maps, precision maps of a particular object versus statistical maps, where you're taking a large ensemble and then measuring statistical properties of those maps. Okay, for point maps, there have been many things tried throughout the years that, I should say, didn't work. Okay, so you can go back in the literature and you can actually find papers where people talk about, like, well, maybe we can look at galaxies and use them as like a standard ruler, where I see this galaxy and measure that it's, whatever angle in the sky, a few arc seconds. Then I measure this one. This one's smaller. It must be further away, right? Actually, it doesn't work at all, right? And it doesn't work at all because galaxies, the range of sizes and luminosities of galaxies is just immense. Okay, so when you make a map like this, it is true that the largest galaxies that you see, sure, those are close by. But the small, faint things, they're just as likely to be at the same distance as this thing as, say, halfway across the universe. So it's just, from an image like this alone, it's really impossible to make any statements. Especially, you can't make any precision statements. Okay, so that doesn't work, although I did find, putting this talk together, I found something going back to 1924 about this. But there are some examples that do work, and most famously, these supernovae that were used to discover dark energy originally. So these aren't used as standard rulers, but as standard candles, where they're not all exactly the same intrinsic luminosity, but they're close, and it turns out they're standardizable in that what these supernovae look like. Some are brighter than others, but the brighter ones actually last longer. And so you can write down a relation that says, well, I know this supernova explosion lasted, say, 20% longer than this other supernova explosion. So in fact, just empirically, we know we can make relations out of these, standardize them, and then use them as standard candle point sources. Okay. Just in the last couple years now, there have been these large compilations of 3 different supernova cosmology groups around the world that have reanalyzed all of their extant supernova data. And this is what the community is using now for their cosmology analyses. So this is really, each of these represents many years of work. At the same time, there has actually been advances in how to standardize these supernovae. So I'm just going to mention one here, which is supernova twinning, which is just taking the standardization to the next level. But it's actually a pretty simple thing to explain, which is you can take a detailed spectrum of a supernova and say, okay, this is what this supernova looks like in excruciating detail. Find me the supernova observation that looks most like this particular explosion. And so just out of your sample of thousands of supernovae, find the one that looks most similar, and then pair those 2 supernovae up. And if you do that, then the standard ruler actually becomes twice as good. So in a statistical sense, it's 4 times more powerful. So you've really pushed down your measurement errors on these supernovae. So that's pretty exciting. The other exciting thing is we're on the cusp of a new generation of experiments that will discover many more supernovae, take better data, and so the largest of these being Vera Rubin Observatory, which actually I meant to check. They were supposed to get their first photon last night. Did they? Okay, all right, okay, so it's operating. So we're already in the new world order here. So this promises much better statistics, so actually millions of supernovae discovered over 10 years of observation, and a better understanding of the instrument and calibrations. Okay. On here. Okay. Now I'm going to move on to the statistical maps. Okay, so this is redshift surveys. These pictures here, this is the first real cosmological redshift survey map being made. So this was done with actually a custom-built instrument in the early 1980s called the Z machine, which you can actually find now in the Smithsonian. It's not very impressive, but it produced an impressive map at the time. So this was our first 3-dimensional redshift space map. So it's called the CFA Redshift Survey, and we call this the Stickman for obvious reasons. So for many years, people would refer to the Stickman map. So now you've seen it. Now you know what they'll be talking about. Okay. And this telescope, it was over many years, they made this map of 2,401 galaxies, where they would measure the redshift to 1 galaxy at a time. And so on a given night, maybe they'd map 10 or 20 or 25 galaxies, just very painstakingly. This was done over many years. Okay. At the same time, since you've finally had a 3-dimensional map, you could talk about what statistics you would be applying to it. So then this was the first application of the 3-dimensional 2-point functions, just looking at the excess probabilities of galaxies being at certain separations from each other. So this was from that very map, the first 2-point correlation function showing that on small scales, galaxies are more clustered than they are on large scales. So this might not look all that impressive. But this guy, Jim Peebles, actually got the Nobel Prize for this a few years later. So he got the prize in 2019. Okay, so he had to wait a few decades. So this was interesting to me because this wasn't like an aha moment prize of like, oh yeah, give that guy the Nobel Prize. But this was really making advances in our understanding of cosmology, but the full power of it not being realized for many years.
So the distance is only information, like there's no weighting. Too much 2-point function not weighted in terms of galaxies, brightness, or size, just the distance.
So there have been many variants of this statistic actually proposed and used, but essentially you don't learn very much more by trying to do different weightings and things like that. In detail, you kind of learn about galaxies themselves. So like it turns out that blue galaxies and red galaxies cluster a little bit differently. And the reason for that is in the center of dense clusters of galaxies, galaxies merge, and all these galaxies that were blue, they actually combine, become red galaxies. Those, all of the gas stops forming stars, and then it becomes a red elliptical galaxy. So so it turns out on small scales, the clustering properties are different. On large scales, they're not at all. Sorry, that was a long answer. Okay. Okay, so that was the CFA redshift survey. But then over the years after that, techniques were developed to do this more on an industrial scale. And so this is a picture of the Sloan Digital Sky Survey, this 2.5-meter telescope in New Mexico. And what this telescope used was fiber optics that could observe many galaxies at once, and in this case, 640 galaxies at once. This was still a painstaking process because for every observation it would make on the sky, you'd make this aluminum plate that would be mounted on the telescope. You'd drill a hole at the location of each galaxy that you wanted to observe, and then there's this team of 6 or 7 people at the telescope that would plug all these fibers into these holes, so they're kind of like switchboard operators. And on a really good night, if you had like this whole system just running well, weather's perfect, moon is down, skies are clear, it could map up to 9,000 galaxies in a night. Okay, and with this, turns out you can make really good movies. Okay, so this is a movie. It's just a 3-dimensional rendering of the data from the SDSS with about 1 million galaxies, where this is the real, every galaxy in that map is actually at its real 3-dimensional location in space. Okay, and then in these maps, you can make these 2-point functions, measure the statistics of the galaxies, but fundamentally, you're testing this against the laws of physics and things like these baryon acoustic oscillations, which they really are, we talk about them as spherical sound waves. That's really what they were. So they really were sound waves in the early universe, exactly. They propagate out, and they propagate out in all directions, and so it does mean these have to be spherical overdensities. If you make a map and you say, well, I'm going to convert my right ascension and declination and redshift into a 3-dimensional map, and you don't do that right, for example, if you say, I don't think there's any dark energy, I don't believe that, then you get features in these maps that aren't, can you see this here? Maybe you can't really see it. You get features that are actually squashed relative to, sorry, can you see that in the back? I can't really see it here. Okay. Well, what I'm trying to show here is spherical overdensities actually become squashed. And that tells you that you've actually done that conversion wrong. And this is yet more evidence like, no, you actually need to introduce this dark energy force to actually recover these 3-dimensional features in the sky. Super cool. Okay. Okay. And then Leach already talked about this, so this becomes a standard ruler then, where these same features that we see at the surface of last scattering, we see in the late time evolution of the universe as these BAO features. Okay. So that was the Sloan Digital Sky Survey. But then 4 years ago, we started operating the next generation of these experiments. We no longer have those telephone plugging operators employed at the observatory. Instead, they've been replaced with robots. I'm sorry. Okay. So on this particular telescope, so this is using a different telescope. It's a larger telescope. There's a telescope in Arizona now, where its focal plane, instead of these plug plates, it still uses fiber optics, but each fiber optic plugs into a robot, and these robots reconfigure which galaxies they're pointed at. So this is going to be most of what I tell you about tomorrow. Okay, but this is just kind of a summary of what this project looks like. And so these blue points here, those are the tips of these fiber optics. Okay, and then what this allows you to do is map 5,000 galaxies, and it turns out we do this every 15 minutes. Okay, so then you get to make bigger, better maps. So that's what we've done. So as of this week, that telescope has now mapped 40 million galaxies in just its first 4 years of operation. Okay, so this is just more showing what these BAO features look like. The difference now is we can actually make these precision measurements at many different epochs through the evolution of the universe. And then we make one of these Hubble diagrams where we're really tracing out from the Big Bang what the size of the universe is, how much these acoustic bubbles have expanded as a function of time. Okay, and then tomorrow what we're going to hear is how these data don't quite fit even our simple dark energy models. But I learned yesterday we're calling this the Wawa model. So they better fit the Wawa model. Okay. Moving on. So Rubin Observatory, this is what we were just mentioning, turned on last night, apparently. So this is a telescope in Chile that won't be making a three-dimensional map. It'll be making images of the sky that we can sort of turn into, I like to call it like a two-dimensional map of the sky. So we get their angles on the sky, and we get an approximation of the distance of these galaxies by their colors. So this promises to make a map of about 20 billion galaxies over 10 years. It is the largest digital camera in the world, so it's a 3.2 gigapixel camera. And yeah, I figured out iPhones in 2043, that's how big your iPhone camera should be. What I also should have figured out is like maybe your iPhone really will be the same size. I don't know. So my claim is this won't actually compete as far as making these precision three-dimensional maps because this information gets blurred out in redshift space, so we don't, in distance space, so we don't really know the distances of these galaxies. So a map where you can see all the structure very cleanly on a three-dimensional map, once you've smeared it out, there's still information there statistically, but it's not the same kind of map as a three-dimensional map. On the other hand, it's a lot more galaxies. So it's trying to make up for that information content with just a lot more galaxies. And fundamentally, it is different because the way that it'll be analyzing those data, it's not just to make that smeared out, terrible three-dimensional map, but looking at the distortions in these maps from gravity. And so I don't have time to take you through all this, but so gravity distorts the shapes of these galaxies by a few %. We can use that information to then recover what the mass densities are that these photons have traveled through the universe. So in fact, this is a way to directly map where the dark matter is gravitationally without having to make any assumptions about like, well, are the galaxies where the mass is and so forth. Okay, so moving on. How are we doing here? We're doing well. Okay. Neutral gas. Okay. So everything we've been just talking about, these are all the galaxy maps. Where galaxies, we can see galaxies out to, I think the furthest galaxy known, now would know this again. I think it's redshift 14 now. Okay, 14. Okay. So a little beyond where I've drawn it here, but there are only a couple known out here. So I'm sure there are more. So these are discoveries with the James Webb Telescope. But at those redshifts, at redshift 14, most of the universe, it's still neutral gas. That's a challenge to map. You map it differently. The only telescope that's really detected kind of the clustering properties of that neutral gas is this CHIME radio telescope. This is in Canada. So this is kind of an unusual radio telescope looking for a hydrogen spin flip transition. And this actually isn't data from CHIME. The data from CHIME looks much worse than this, okay? But just making the point, it's not making the same kind of maps that we make by mapping out galaxies. It's making a much more smoothed out map of where the neutral hydrogen gas is. But it can do this. CHIME is actually operating at the same redshifts as these other projects. But eventually, you can build these things where you can map out at higher redshifts. And so this is what this square kilometer array, which hasn't been built yet, so this is an artist's renditions. There have been pilots of this project built. But this is a whole radio survey that's meant to be mapping hydrogen gas. It would see all of the galaxies that we're seeing with these optical redshift space maps, although that part of the project, I claim, might not be as interesting if we've already mapped them, because once you map it, you're kind of done. But this project would also be able to map the hydrogen gas out beyond redshifts of 5 and 10.
Is there a proposed site?
It's several sites, and so I think South Africa, Australia, and the Netherlands. Someone else might know. Do you know? Anyway, but I don't follow it that carefully because it's a huge international collaboration, except for the US. Okay, but I'm going to show you something that the US is doing. So this is a NASA DOE joint mission to actually send a radio telescope to the far side of the moon. So this is actually, it's part of the Artemis project. It'll be the first NASA mission going to the far side of the moon, meaning the side of the moon that we never see, launching on Christmas Day. And it's just a pair of dipole antennae. So pretty simple instrument. And actually, most of the payload here is just a big giant battery. I don't think we'll learn very much from this first instrument, because you can see it's not very much. On the other hand, this is to start developing the technology and to see if it's even technically feasible to actually measure these dark ages of the universe out at redshifts of, this is beyond redshift of 30, which from the ground within the Earth's atmosphere would be almost impossible to do. Okay, the CMB I don't have to say as much about because Licha has already covered all of this. But Planck was the most recent space-based CMB mission that ended 6 years ago. 6 years ago, something like that. Simon's Observatory, this is a ground-based CMB mission in Chile that's just started this year. One thing I do want to say about these CMB experiments, though, is they have completed mapping what you can as far as the linear modes at the surface of last scattering. So when you see these beautiful CMB maps on scales smaller than something like the circle, what you have is photon diffusion, otherwise known as silk damping, that's erased any of the early universe information on those smaller scales. So you could keep getting better and better CMB maps. That's not the information you're getting. You've actually saturated the information content. This is merely a two-dimensional slice of the universe. You've already measured it. So in fact, oh wait, okay, but there is an exception. You can get more information if you wait 10,000 years, so that would be a way to do it. And that's just because then you're seeing a portion of the universe that's a little bit further away. So you just have to wait for that silk damping scale to free stream by you, and then it's like, oh wait, I'm seeing a new picture. So that's how you can get new information. Okay, so put a note on that. So these CMB maps, what they will be doing though is actually seeing the structure of the universe at lower redshifts, primarily redshifts 0 to 5, just from the gravitational lensing induced on these maps. So this is very analogous to what this Rubin Observatory is doing, but with a backlight at a redshift of 1100. So I see this and I'm like, man, that's a hard way to make a map. But it can actually be done, and it has the same advantage that you're actually mapping where the dark matter is directly. Okay, then finally, neutrino background. So this would be the snapshot of the universe at 1 second old. I was trying to think of how you'd actually measure this. So we've actually not detected any of these very low energy cosmic neutrinos yet. In principle, you could, if you took a neutrino detector, accelerated it to near the speed of light, then they would appear more energetic. So this was my answer to how to measure the neutrino background. These are big detectors, so I think it's a challenge. Fortunately, there are smarter people finally learned about this morning. So I guess there are other potentially experimental techniques to actually detect this, but I'm just showing this. Again, I only just learned about this morning. Okay. Okay, a little bit more time. So these are kind of the standard probes that we've been developing over the last 25, 30 years. There are some novel probes that might actually make a difference in the coming years. So I just want to at least walk through what these might be. So one is, this is a telescope that's being built in Chile by the Europeans. The extremely large telescope actually goes on sky in the next year or so. So this is the first telescope that's large enough where on paper you can actually measure V dot for galaxies. So not just their position in space, but if you observe the same galaxy and then observe it again 1 year, 10 years later, you'd statistically have enough information to actually look at the acceleration of individual galaxies as a function of time. Whether we learn anything from that, I'm not sure, but it's in principle measurable. Okay. Kinematic lensing. So this is a technique that's people have talked about, has not been implemented yet. But this is making these shear maps of galaxies, but to actually use spectroscopic information to know intrinsically what each galaxy actually looks like, so you can make a more precise determination of how much the shape of each galaxy has been distorted by gravity. So again, this hasn't really been employed yet, but in principle, this is something that could take these big maps that we'll be getting in the next few years and actually increasing the signal to noise in those maps by a factor of 10 or 20. So that could be exciting. Standard sirens. Okay, so this is the fact that now we can detect gravitational wave events from LIGO and the gravity wave detectors. These gravity wave events, from the detections, you actually directly measure what the distance is to these things. So if you compare that distance to the redshift, then in principle, that's your ideal Hubble diagram of what's distance as a function of redshift. The problem is, most of these events like this, two supermassive black holes coalescing, makes a strong signal gravitationally. You don't actually see anything electromagnetically. So this is one of those things where, in principle, it would give you kind of a perfect Hubble diagram. In practice, you have to be able to see it, or you can't do anything with it. You know the distance, but it's invisible.
How about the mergers of neutrons?
So yes, so neutron stars, if you could see them distant enough and then see their counterparts, that would be a way. You'd have to localize it enough to know which galaxy it's coming from. And the localization, like this event here, I think the localization was to within something like 1,000 square degrees on the sky.
We're getting a lot of new gravitational waves.
Right. And once you get more detectors, you'll be able to localize better, so then you localize more to degree scales. I think the hope here is that this turns into a statistical problem where you make a map of where all these gravitational wave events are. You have a big localization area of where it is on the sky, but then we're still making maps of galaxies, so they know those are going to exist. And then you need to align these maps. So again, like figure out what the scaling is as a function of distance so that you can align these maps. Now I'll say this was a kind of an early paper talking about this, saying we can actually use these maps then, get a 2% measure of the distance scale at redshift whatever, and they promised to do that within 5 years in October 2018. So often we misjudge by a little bit, but keep your eye on this space because it still could happen. Okay, strong gravitational lenses, another super cool effect. So we've talked about gravitational lensing a little bit, but strong lenses, these are where you have a mass concentration that's great enough that we actually get multiple images of the same object in the sky. So the idea of using these as a geometric probe dates back to Refstol in 1964. What's happening recently is, until recently, we only had small numbers of these strong gravitational lenses actually discovered. In the last 5 years, this has now exploded into thousands of these gravitational lenses. So this is the advent of these big surveys that are being undertaken. So I think the count now is, well, again, it's at least in the many thousands. And in those, then you can find some really interesting objects that could be a Rosetta Stone as far as measuring relative distances to different galaxies. So this, I'm just going to show you 3 of these events that have been published in the last year. This is something called the carousel lens. This is actually an alignment, a near perfect alignment of galaxies at 7 different redshifts. And then they're all gravitationally lensing each other. Here's a strong lens where they named this after that same person, Refstol. A strong lens where they actually saw a supernova explosion appear in the several images of the background galaxy. And then here's yet another supernova explosion seen with the James Webb Telescope, again, in different images of the same galaxy. Okay, so I'm done now talking about mapping. I've taken you back to the first second of time, so now we're just going to go to the first second of time for the end here. So this is the inflation epoch. So this, as Lecha talked about, we've postulated, it was postulated that there is this inflationary potential in the first fraction of a second of the universe that would explain the homogeneity and the isotropy of the universe. So this was first postulated in 1981, but besides these general observations, until recently has really been beyond the scope of any sort of experiment you could hope to do. But here's another case where they did eventually get the Kavli Prize, but they also had to wait 33 years for this. But this is something that we can now explore today. And so one of the things that we can measure is from these CMB maps and these galaxy maps, we can actually ask, what's the fluctuation power spectrum look like in the early universe? And one of the interesting discoveries is it's not a purely scale-free fluctuation spectrum, meaning there's kind of a tilt to it. And what this means is if you challenge this versus different models for inflation, I mean, it doesn't fit necessarily the very simplest models of inflation. One way to look at this question, though, is so we have this inflationary epoch in the early universe. So this was something where the universe had an accelerating expansion, and then that expansion stopped. So this appears to be another force that persisted, was dynamic, and then turned off. Dark energy is this force that we see today that's pushing the expansion of the universe. So in some, empirically, what this looks like is kind of a similar sort of force, where something that is pushing on the expansion of the universe. So I guess I have this secret dream that it's the same force, that maybe from a point of view of simplicity, maybe this was a force that turned on, turned off, now it's turned on again. But we'll see. We'll learn more. There aren't a lot of tools for measuring what happened at this inflationary epoch, but these different theories of inflation, they seem to predict that either we will see something in these CMB maps where we'll see the imprints from the primordial gravitational waves on these maps, or we'll see something on these maps of galaxies in terms of the non-Gaussianity features in these maps. So this next generation of experiments really is impinging on the different areas where these inflation models predict to see something. Okay, and then there was a NASA satellite just launched a month ago, SphereX, where it is designed explicitly to try to see these features from inflation. So I'd keep your eye on this. But if this doesn't, we do have future experiments coming after this. Okay, so I'm going to end here, but I hope I gave you a flavor of the experimental landscape, which has really progressed phenomenally just in recent years, and we're really at the cusp of this next generation of experiments. So Rubin, I said, starting this year. I guess it's starting last night. That's great. All of these redshift surveys. DESI is actually only the first. There are a number of others starting in the next year or two. So we'll talk about those tomorrow and what we're already seeing in those maps. And I fully expect over the next several years, we'll be mapping all of the linear modes, so these primordial features that the universe has given us in out to redshift 1, and we'll start making these equivalent maps or better maps out in the more distant universe. Okay, so I'm going to stop right there.
Okay. Well, first of all, thank you for this really wonderful talk. Can you clarify what you really mean by a 3D map of the universe? What I'm getting at is that the data are redshifts, and right, and positions on the sky. So in order to actually build this three-dimensional map, one, you need a expansion history of the universe, right, that you believe in, and presumably these galaxies have evolved, and at least naively, by 3D map, you mean a map of things that are all at the same time, right? So can you just clarify what you mean by that?
Yeah, so actually there are a couple questions there, both good questions. So one is, when we make these maps, you're absolutely right. This movie I'm showing here, so it's a map where fundamentally this map is angle, redshift, and that's our map. And so you actually have a choice. You can say, well, let me take my model and make it agree with that map. And then you take a model for the clustering of galaxies and say, OK, now I'm going to translate that into angle, redshift, measure the compressed statistics on that, like the 2-point function, and see if they agree. Typically, we don't do it that way. We do it the other way around, where we say, OK, let's take this map. I'm going to assume that there's 68% dark energy today and however much dark matter. I'm going to put in those ingredients, and then that gives me the information I need to know to then convert redshift to distance. So then I measure the clustering in this map in real space and compare that to the models. And then you can update that and say, well, what if dark energy is a little bit different? Let me do that conversion, make a new map, and make the comparison. So you can do it from either direction, but you're absolutely right. That's what you're doing. And fundamentally, that's what we're trying to do, is then figure out what are the model parameters that actually make that consistent. Your other question was a good question of, we make this map. It's spanning a large range in time, right? So, and in fact, clustering obviously is evolving with time. So galaxies are more clustered today than they were at high redshift. And in detail, it's more complicated than that. So like these acoustic features, they're mostly frozen in from the early universe, but gravity is actually evolving them a little bit. So you have these spherical overdensities, but as time goes on, the overdensities, they're gravitationally attracted to each other, actually smooths out those features a little bit in a predictable way. Anyway, but to come to answering your question, in practice what we do is we take those maps, we slice it up in redshift, and then we do our analysis in different redshift bins. And those slices, typically they're small enough that we can ignore the fact that there's evolution from one edge of that slice to the other edge of that slice. And if it does matter, you can put that in as correction terms of, well, I know, there's however much evolution between redshift of, say, 0.6 and 0.7, and then include that in your model. But yeah, you can't ignore that. That's right.
Sorry, so you did explain how you do 3D mapping of using your telescopes. How is that fundamentally different from the slide you explained where you are using essentially a 2.5 dimensional mapping? And what kind of differentiation in techniques does that actually involve?
Yeah, so I'm going to take you through the details of that tomorrow. So the question is how you make a 3D map, these 2.5 degree maps. So, but in short, something like the Rubin Observatory, which is, it's only measuring the colors of galaxies in 6 filters. So it's kind of like a spectrum of a galaxy in 6 colors. Galaxies, they change color as you redshift them away. And so you can sort of estimate what its redshift is based on its colors. That works well for some galaxies. It works really, really badly for other galaxies. So you try to select a sample of galaxies where it kind of works. These 3D maps, it's very different, where each galaxy, we take its light, and then we send it to a spectrograph where we're actually dispersing the light into something like 10,000 different colors. So it's a very, pretty high resolution spectrum of that galaxy. And there are features in the galaxies where we can measure the redshift to its a precision of typically a part in 10 to the 4. And again, I'll show you that tomorrow.
You said you had a dream that possibly inflation and dark energy turn out to be like the same force that turn off and on or at different times. Does it seem like that's now possible with new evidence of time-varying dark energy, or they still seem too distinct? Or
So that is a question for the theorists in the room.
Okay.
So I don't know. This is, I just say that as like my dream as an experimentalist. Like, hey, we got these two very funny, weird things. Maybe it's the same thing.
So when you're measuring the BAO feature in the map of galaxies, most of the statistics is focused around the first peak of the BAO, but there are harmonics. Can you just give me a quick flavor of why it's not useful to go to the higher harmonics and use that extra information to further constrain things?
Yeah, so it's well, maybe Leacha would be better answer this, but in real space and oh, go ahead. Go ahead. No, you take it. So for these galaxy maps, it's in real space, or what we call configuration space. It really is just there are these spherical overdensities. We don't see harmonics of that in real space. Once you take the Fourier transform of that, we see the harmonics in Fourier space. But that's just really an artifact of a Fourier transform of these real space features. The CMB is actually a little bit different than that, but that's where I'd defer to Leacha.
Such a high signal to noise that the detailed property of the oscillation, not just the position of the scale, but also the ratio between odd and even peaks and all that, adds a lot of information. In the case of the BAO in the galaxy distribution, that signal is much, much smaller because it comes from the baryons that are much less than the dark matter. And therefore, most of the information just comes from the location. Forget about the overall shape. There are no linearity there. There's a lot more. I'm not saying that there is no information. I'm just saying that the bulk of the information can just from the location of the feature.
So I will add, it would have been very different and super cool if there weren't dark matter, if all the dark matter really were baryonic matter. And so I'll go back, when I was a student, this was my dream. It's like, I bet it's all baryonic matter. There's not any dark particles. But we didn't have the data there to really say very much. So it could have been, if it were all baryonic matter, then in the CMB, we hadn't measured this really yet, the fluctuations would have been way more dramatic and then would have imprinted of order unity in the baryon distributions. And then these maps that we're looking at today, these features that really are just few percent over densities in galaxies would have been of order unity, just like huge overdensities. It would have been a very cool, dramatic map. That's not the map we have, though. So that's kind of part of the evidence of the dark matter wasn't tightly coupled to the photon plasma.
So I just feel like there is a really lack of the neutral gas area detection thingy. So what is is that have any other prospectus the the future or some kind of the related to the the dark matter detection or sorry, I have hard time to organize my question. So
Yeah, so if we go back to these neutral gas measures, so one thing is experimentally it's a very hard thing to measure. So you need, this is a huge array, not really big enough to do precision science with yet. What you'd really like is something that looks more like this. But there's the additional problem of like, even in principle, if we could get the perfect data, we don't actually know how good of a map this would ever deliver. And that's just a function of what the backgrounds are. It's more analogous to the microwave background, where the microwave background signal, it's a small signal relative to foregrounds. Here it's kind of the same thing, and we don't know how good these measurements are going to get. So we don't really know until they're done.
okay.
So if we have time, can I ask a question? So it's it says something that a 2.5 meter telescope was considered, among the best telescope ever, even above HST, and even better than the 10 meter telescope that are available and were available. So when the Sloan was being planned, what was keeping you up at night, and what ended up keeping you up at night in reality? Was it the same thing? Was it a different thing? There was probably more than one thing. But
The Sloan telescope, there are a lot of stories about the Sloan telescope. The Sloan telescope, it was really the first large...
By telescope, I mean telescope spectrograph, the whole thing.
The whole thing, yeah. It was built as a unit, the telescope and the instrumentation and everything. But it was a big collaboration of people around the world, and at the time, I think it was the most distributed project. And so the issues that we had were really more in how to, we had lots of technical issues because it was breaking ground on a lot of things. But the issues, I think, more had to do with figuring out how to actually do science in this community as kind of a large collaboration, where up until then, like CFA, redshift survey, you send a person to the telescope and they take data, and then maybe you have 2 people look at the data once you're done. And then Sloan was a collaboration of several hundred people. So I think that was really, I think, the big change there. And I'd say today we actually know how to do that. So we do, I think, for cosmology, where the field is very much dominated by these large projects where it is the people who have figured out how to do this. But yeah, Sloan almost failed many ways. Though I should say, the way that it was very good was this hand plugging of optical fibers. That was just engineering. People could write down the engineering specs, and that just worked. So that worked phenomenally well. So tomorrow, we're just going to talk about these 3-dimensional maps. That's what I spend my time doing. So I'm going to walk through the DESI project and how we actually designed and constructed that instrument, and then how we analyze the data, and how we get a 3-dimensional map out of the end. And I'm going to talk a little bit about what's next. Yeah.
Let's thank David again.